Now we're going to go through the open mapping theorem. Section 3.3 is, the title is open mappings, but it's all about the open mapping theorem. There's only one result in this section, but it's going to take us a while to get through that one result. We'll give a proof of the open mapping theorem, which states that onto, or surjective, bounded linear operators map open sets to open sets. Quick observation, there's plenty of mappings that don't map open sets to open sets, including some continuous mappings. A continuous function need not map an open set to an open set. If it's not one-to-one, it's not too complicated to map an open interval to a closed interval. Take a sine function, for example. Sine function from open interval from 0 to 2 pi will map that interval to the closed interval from -1 to 1. Open set in, closed set out, and you're dealing with a continuous function. We've stated how continuous functions interact with open sets. It's the inverse image of open sets that are open with respect to continuous functions. So anyhow, this is a little bit of a claim here, a situation where open sets are mapped to open sets. We need a preliminary lemma. We'll use these pieces of the lemma throughout the proof of the open mapping theorem. The setting is normed linear spaces X and Y with subsets A and C of space X and alpha as a scalar. Let T be a linear transformation. Then we have alpha times a ball of center 0 and radius R. We've used this notation in passing, but let's reiterate. Sometimes that's just abbreviated B of R. It's understood when you see B of R that you're dealing with the open ball and that the center is 0 and the radius is R. So alpha B of R is claimed to be the same as B times the absolute value of alpha R, which can also be written like this, which makes perfect geometric sense if you think in terms of Rn or just R2. What you're doing here is you're multiplying all vectors of norm less than R by scalar alpha. Well, that's going to produce a vector of norm absolute value of alpha times the norm of the old vector. So of course you get all vectors of norm at most absolute value of alpha times R. Oh, and using the absolute value, whenever we've done this, it's understood that that scalar field would have to be the reals or the complexes where absolute value is defined. Secondly, if we take alpha times the closure of a set, all these things are defined. We've multiplied what it means to multiply a set of vectors by a scalar. It means to multiply every vector in that set by that scalar. Alpha times the closure of set A is the same as the closure of the set alpha A. The closure of alpha plus the closure of C, the closure of set A times the closure of set C is a subset of the closure of the set A plus C. In the real setting, we could get equality on this. But subset inclusion is the claim. And if we take transformation T, linear transformation T, and apply it to set alpha times A, set alpha A, alpha being a scalar, the scalar comes out front. Yeah, well, that shouldn't be much of a surprise there. You can bring scalars outside of linear transformations when applied to a scalar multiple of a single vector. And what alpha set A means is alpha applied to all the vectors in set A. So no surprise there, really not a surprise with any of these. The proof is to be given in one of the exercises in this chapter. And now for the star of today's discussion, and the last thing we'll look at, though it's going to take us a while to get through this. The open mapping theorem says, given a surjective, that is an onto, bounded linear transformation, where X and Y are Banach spaces, if U is an open set in Banach space X, then T of U is an open set in Banach space Y. So hypotheses are surjective or onto, bounded linear transformation. T is bounded. That wasn't mentioned in the lemma, but we need it here, and we'll see where. And X and Y are Banach spaces. So there's completeness with the X and the Y. So let's go through the proof with an eye towards using all of those hypotheses. So we'll keep an eye on where surjective, onto, is used, where bounded is used. Linear will be used throughout whenever we use that lemma, that required linearity. So the linear is not a surprise. Boundedness, we'll keep an eye on where we use that. And a Banach space, whereas the hypothesis that both of these are Banach spaces is used. So claim is open sets transform to open sets under bounded linear transformations, which are surjective. The book breaks this into 3 steps. I'm going to follow the book's presentation. The first step is really the conclusion, but we're going to, well, here's step 1. Suppose that we have shown that T of the unit ball contains a ball centered at the origin of radius delta for some delta greater than 0. And that's what we're going to do in the following 2 steps, in particular in the 3rd step. So suppose we've established the existence of an open ball that's a subset of T, the transformation applied to the open ball of B of 1. Quick thing to maintain some sanity throughout what follows. We have 2 Banach spaces. All right, so we could have open balls from one Banach space or the other Banach space. We need something different to distinguish between these. Different Banach spaces will have different norms. So when I say a ball of radius 1 versus a ball of radius delta, well, this one comes from Banach space X, and so is based on the norm there. This one, being a transformation, must involve a ball in Banach space Y. So the shorthand is when you see a prime on the B's, it's talking about balls from Banach space Y. No primes, balls from Banach space X. So suppose, because we're going to do it in the following steps, we've shown that T of B of 1 contains the open ball B prime of delta for some delta greater than 0. That's the only information we need to show that if U is open in X, then T of U is open in Y as follows. Establishing that is going to take a while. Given any open U, a subset of X, let Y be an element of T of U. So we have Y equals T of X for some X in U. That's simply what these things mean, using the lowercase letters in very suggestive ways as to which Banach space they're from. Since O is open in X, there's an R greater than 0 such that U contains a ball centered at X of radius R. In other words, this X that's an element of open set U is an interior point. That is, there's such a ball of radius R that's a subset of open set U. Well, a ball of center X and radius R can be rewritten using the lemma 3.4 properties as vector X plus R, scalar, times a ball of center 0 and radius 1. All right, makes good geometric sense. We'll actually draw a picture before this thing's over with. But one reason to like analysis is you can draw lots of pictures, but think what's happening. Here we're taking the unit ball. We're multiplying it by scalar R. You might want to think R is little. All right, so we're taking the ball of center 0 and radius 1, and we're shrinking it by a factor of R. So ultimately, we could think of that as a ball of center 0 and radius lowercase r. That's what you get out of this piece of it. But we're taking r times that unit ball. We could also represent it as r times b of 1, the b of notation. And we're simply translating it to point x. So we're taking really a ball of radius lowercase r, and translating it from the origin to point x or vector x, and that produces this ball. So it's a two-step geometric process here. Shrink it by factor r, and then translate it so that it's centered at x. But the lemma justifies these manipulations, and they're very geometric, so not surprising things. So we've got U contains x plus r times b of 1. Then T of U contains T of x plus r times b of 1. Maintain the subset inclusion when you apply the transformation. Linearity allows you to write this as T of x plus T of r times b of 1. Scalar r comes outside of the transformation, even in the set setting, because T is linear. We've denoted T of x as y equals T of x, so we pick up a parameter y there, so that's just substitution. And we've said, suppose this has been shown, so the T of b of 1 that we have right here contains this open ball b prime of delta. So the T of b of 1 contains the b prime of delta. Simply do a substitution there. You pick up a set inequality. And as we said in lemma 3.4 part A, I can take the r inside. We could have done that earlier. We've done it here. Take the r inside, and this can be written as y plus b prime of r delta. So a ball of center y and radius r delta in Banach space capital Y. The prime tells you the ball is in capital Y, and we chose lowercase y to be something transformed. So something in Banach space Y. And as I stated, this is a ball of center y and radius r delta. So T of U is open. Open means every point is an interior point. So what we did is we chose y, an element of T of U, an arbitrary point in T of U, and we found a ball centered at y of some radius that was a subset of T of U. In other words, arbitrary point y is an interior point of this set T of U. If all the points are interior points, then that's an open set. So there's the conclusion, T of U is open. But all of this done on the supposition that we can do this. So 2 more steps, some pictures, and a lengthy argument. The big goal is to find an open ball in Y that's a subset of the transformation applied to the unit ball from Banach space X. B prime of delta is subset of T of B of 1. Okay. So step 2, let V be the transformation applied to a ball of center 0 and radius a half. It's T of B of a half for some reason. So not very inspired, but there's the construction. V is the same as negative V. If you take a ball centered at the origin of all vectors of norm less than a half, you multiply all those vectors by -1, you get the same collection of vectors. You still get the same ball since it's centered at 0. So V equals negative V, an observation we'll need. For any Y in Banach space Y, since T is onto, we're going to keep track of when hypotheses were used. So there's the surjective or the onto hypothesis used right there. For any Y in Banach space capital Y, there's some X in Banach space X such that Y equals T of X. Now, by the way, we could take any non-zero scalar, let's call it 2K, insert a 2K here and a 2K here. We get equality. The linearity says this 1 over 2K comes outside of the transformation to cancel with that and leave you with just T of X. So why do you want to do that? Well, we're going to be cutting some things in half. That's why the 2 parameters been introduced. So if we have the norm of X strictly less than K, then the norm of X divided by 2K is strictly less than K divided by 2K, or strictly less than a half. So here we have a vector of norm strictly less than a half. In other words, this vector is in B of a half, the ball centered at 0, and with radius a half. That is, x divided by 2k is an element of a B of a half. The ball of radius a half and center 0 consists of all vectors of norm strictly less than 1/2, and that's what this vector satisfies. So y is an element of 2k t of B of a half. Let's dig through that. So what we're going to do is apply the transformation in some sense to both sides of this equation. On this side, we'd have t of x divided by 2k. That would be t of x, or y, divided by 2k. Take the 2k to the other side, and then when on the other side, we'd have the 2k picked up, transformation applied to B of a half. So y is an element of this particular set. We had denoted B of a half with a capital V a while ago. So this gives us y is an element of 2kV. So 2k, that's some, we brought it outside of a transformation. Let's see, set, well, it ultimately, it doesn't matter whether k is positive or negative by this observation up here. Let's take it to be positive. So without loss of generality, that can be done. And so we've got y an element of some positive integer times v. Y is an element of nv for some natural number n. Y was an arbitrary element of Banach space capital Y. So we've shown the whole Banach space, then, since each element lies in some n times v, the whole Banach space must equal the union over all indices n of n times v. So we've written the whole Banach space as a countable union of these things here, these n v's. We're going to consider the sequence of closed sets n times v, nv closure. Sum from n equals 1 to infinity, a sequence of sets. And we're going to use something related to Bayer's theorem, actually the dual of Bayer's theorem. All right, if, and this is a big if, in fact, it's wrong, if each closure of nv, and that can also be written as n times the closure of v, if each of these has an empty interior, then the union has an empty interior. Corollary 3.3, the dual form of Bayer's theorem. Bayer's theorem dealt with open dense sets. The dual was a closed set with an empty interior. And what we showed in the dual form of Bayer's theorem is if we have a countable collection of sets with an empty interior, then their countable union has an empty interior. So what we get from that is, hey, that countable union will have to have an empty interior, but that's the whole Banach space Y. So that implies Banach space Y has an empty interior if all of these things have empty interiors. That can't be the case. A Banach space can't have an empty interior. The whole set Y is an open set, and there's something there. There's something in Y. So it's also a non-empty set. So if the whole set is open, then the whole set is its own interior, and you've got the zero vector in a Banach space, for example. The Banach space is non-empty. This gives us a contradiction. We can't have a Banach space with an empty interior. The whole thing is open. Anything inside it would then be an interior point of the Banach space, and there's things inside it. So that doesn't work. We can't have all of these things, these NV closures. We can't have all of these with empty interiors. So there's one of them that ain't got an empty interior. So there's some natural number n such that n times the closure v has a non-empty interior. So pick yourself something in the interior, call it W very briefly. W is the form n times y. Right, we've chosen something in V closure. Remember, V was the transformation up here of B of a half. So anyhow, it's the V and V closure are vectors in Banach space Y. So n times Y equals W for some Y here. And this is an interior point of n times the closure of V. It must have a non-empty interior. There's a thing that's in that interior. So if we have ny as an interior point of n times V closure, in a very crude sense, we can cancel the n's and draw the conclusion that y is an interior point of V closure. So what's it mean for y to be an interior point of V closure? For some s greater than 0, there's a little ball of center s, of center y and radius s that's a subset of V closure, the very definition of interior point. A ball of center y and radius s, a B prime ball, because this is stuff that's happening in Banach space Y, and that's where we use the prime notation. And we've taken that B of y semicolon s ball and written it in terms of a translation of B prime of s. All right, how are we doing? What are we looking for? We're looking for B prime of delta, an open ball that was a subset of the transformation of B of 1, previous slide. So this ain't it. But anyhow, we've found something that's small. Y plus B prime of S is a subset of B closure. One more time. Y plus B prime of S is a subset of B closure. Let's draw a picture. Okay, so here's a picture. Some things going on in Banach space Y. How can you tell? I see the primes and also the V closure. See negative V closure, same thing. So this is definitely a little image that represents behavior in Banach space capital Y. Suppose you chose a Z in B prime of S over 2. We're going to show something about that Z. And before it's over with, hey, there's B of 1. Actually, there's T of B of 1. That's of interest. So we're getting a little closer. So choose a Z in B prime of S over 2. Here's B prime of S over 2, ball of center 0. So here's the 0 vector, the origin, if you want to think about it geometrically. That's, if you're careful, that's a good idea. So here's what we have as a representation of B prime of S over 2. There's point Z, it's inside that ball. The claim is negative Y plus Z is an element of negative V prime, which is the same, negative V closure, which is the same as the closure of negative V, which is the same as V closure. We've mentioned all this stuff on the previous slide. The claim is negative Y plus Z is in V closure. Here's Y. We left off on the previous slide, so I repeated it a couple of times. Y plus B prime of S, representing that as this ball here, twice the radius of this ball over here. So actually, try to draw it to scale. This thing here is a subset of V closure. So if we go to point Y and we add to it point Z, hey, point Z is a little bitty vector of length norm, less than S over 2. So when we look at Y plus Z, that'll give us a new little vector here, and it's it's less than halfway to the edge of this circle. So certainly Y plus Z lies inside V closure. In fact, it lies inside this ball here. You could even look at Y plus 2Z, and that would still be in V closure. Z is of length less than S over 2, so 2Z is of length less than S. And I can imagine drawing little vectors that represent distances in some sense. Hey, you add 2Z, you're still going to be inside the B prime of S ball centered at Y. So a little geometric picture to make some sense out of those algebraic claims. We've considered negative y plus z and y plus 2z for reason. Z itself can be written as y plus 2z minus y plus z. Cancel the y's, cancel one of the z's. Yeah, that arithmetic checks out. All right, y plus 2z is in V closure. In V closure. Negative y plus z is in V closure. So we get that this is an element of V closure plus V closure. When you add two sets together, add the closures of two sets together, you get a subset of the closure of the sum. Lemma 3.4 part C said that. V, remember V by definition was B of a half, previous slide. So let's substitute that in. No, excuse me, it was T of B of a half. So let's substitute that in. V equals T of B of a half. That's what the V parameter was introduced to represent. So we get substituting T of B of a half plus T of B of a half, closure of. You got a linear transformation here. Transformation, well, sum of the transformations is the transformation of the sum, and that even works for sets of vectors. B of a half plus B of a half, that's taking any vector of length at most a half, norm at most a half, and adding another vector of norm at most a half to it. That's going to give you all the vectors of norm at most 1. B of a half plus B of a half equals B of 1. So we've got Z is an element of T of B of 1, closure. We're trying to show T of B of 1 contains an open subset. Here's what we have at this stage. The closure of T of B of 1 contains all Z in B prime of S over 2. That is this little ball here. So T of B of 1 closure contains this little ball. We were trying to show T of B of 1 contains a little open ball. Oh, we got the closure in the way. So we'll spend some time getting rid of the closure. So if we take R equals S over 2 was the radius of this little circle from which vector Z came from, then we have B prime of S over 2, that is B prime of R, a subset of the closure. We took an arbitrary point of B prime of S over 2 and showed that point Z was an element of this thing here. So the whole ball, B prime of S over 2, is a subset of this thing here, the closure of T of B of 1. So if we can get rid of the closure thing, then we're done. This is not what we were trying to show. We were trying to show B prime of delta is a subset of T of B. Let me step aside very briefly. I don't often look at what I've set up as the print files, but let's get this in the background. So here's the slides we've gone through so far. Remember step 1, this was the goal, to find a delta such that B prime of delta is a subset of T of B of 1. We've got an R and we've got a closure. So we're pretty close. And this is analysis, so we've probably got some room we can wiggle around with, make this radius smaller and take care of that closure thing. And that's how the story will end. Step 3. Okay, we have B prime of R, a subset of the closure of T of B of 1. For some R greater than 0, it was S over 2. We had to do some cutting in half to get that kind of behavior. For any non-negative integer k, we have 2 to the negative k, B prime of R, is a subset of 2 to the negative k closure of T of B of 1. And all we did was multiply both of these sets by 2 to the negative k. Subset up here will imply subset down here. We can take those constants, 2 to the negative k, inside the B prime ball and the B ball, as described in lemma 3.4 part D. Take a ball of center 0 and radius R, multiply all those vectors by 2 to the negative k, and that produces a ball of center 0 and radius R divided by 2 to the k. It just, K was positive. It shrinks the radius down. So that should make good geometric sense also. And the same kind of things happening on the other side, except we got the closure thing involved there. So we got B prime of R over 2 to the K, a subset of the closure of T of B of 1 over 2 to the K. Okay, so this is a bit of a lengthy argument still. Remember, it's T of B of 1 we want to talk about, and we were close. Now we wandered off talking about something else, but we got our reasons. How we doing on using hypotheses? We've used the fact that U was open. We used that in step 1. We've used the surjective, the onto part. We haven't used the Banach space part yet. So in what follows, we're going to create a sequence of something. So it would be it's a sequence of sets, but we'll use a property of Banach spaces. So it's coming, and that's where this stuff is leading. All right, so B prime of R of 2 over K is a subset of the transformation applied to B of 1 over 2 to the K, closure. So for any Z in B prime of R over 2 to the K, any Z in here, that Z is also in here. What does the closure of a set consist of? Well, the elements of the set, so Z is either in T of B of 1 over 2 to the K, but the closure also consists of limit points of that set. So Z is either in the set, T of B of 1 over 2 to the K, or it's a limit point of the set. Theorem 2.2.A tells you that. You might have to piece together a couple of little pieces to word it in terms of limit points. It speaks of boundary points and various things. But either we get Z is in the set or it's a limit point of the set. And Theorem 2.2.A will justify that. So give me some wiggle room. Any epsilon greater than 0. If T is a limit point of that set, then there exists an X and B of 1 over 2 to the K. Such an X, when transformed, T of X will be in T of B of 1 over 2 to the K. So there exists an X in this ball such that T of X is within epsilon of point Z. Now, if Z is actually in T of B of blah, 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 if it's in the set, we can actually make this norm 0. And that's less than epsilon, ain't it? But if it's a limit point, then I need the wiggle room of epsilon. So anyhow, with the epsilon, this can be done. This inequality can be satisfied, whether Z is in the set or Z is a limit point of the set. So such a X can be chosen. Choosing the X's in balls in Banach space X and then transforming them. So what norm is this? Just to keep track of things, this would be the norm on Banach space Y, because Z is in Y, you know, from the prime, and the transformation takes X's from Banach space X and produces T of X's in Banach space Y. T is a bounded linear operator from X to Y. I don't think we've used the bounded part yet either. All right, so this little observation here, we're going to iterate as follows. Suppose Y is an element of B prime of R. So we've taken an arbitrary element of B prime of R. That sounds pretty good. Maybe this will be the B prime of delta that we're looking for. Almost. We're going to do a little bit of cutting some things in half one more time. But we're taking Y as an arbitrary element of B prime of R. Choose X1 in B of 1 such that the norm of Y minus T of X sub 1 is less than R over 2. So that's what we have up here, where we're taking K equal to 0. So we're considering X an element of a ball of radius 1 over 2 to the 0. That'd be B of 1, right? The X value, X sub 1, is chosen from B of 1. and we're making the norm less than r over 2. So we're taking the epsilon value to be r over 2. So we've chosen an x1. Do it again. So y minus t of x1 is an element of b prime of r over 2. It's a ball. Let's see, y was in b prime of r. Let's see, t of x1, here we go. T of x1 is within distance r over 2 of y. So we can draw the conclusion that the norm of y minus t of x1 is less than r over 2. That means that vector is in the ball, centered at 0, of radius r over 2. It's a lot of moving parts. So we get this to hold. Now, do it again. Choose x sub 2 in a ball of radius 1/2 and center 0. So we're choosing the x like this with k equals 1, such that this vector, y minus t of x of 1, this vector in b prime of r over 2, that's playing the role of z, that vector minus t of x2 in norm is less than r over 4. Taking k equals to 1, 1 over 2 to the k, 1/2, and epsilon is r over 4. Epsilon is r over 4. Observation. Here you've got a vector of norm less than r over 4. And it's a vector in Banach space y. So this vector, y minus t of x of 1 minus t of x of 2, that vector is in b prime of r over 4 because it's norm. It's y Banach space norm is less than r over 4. So it's within r over 4 of the origin. It's a vector of norm less than r over 4. It's in b prime of r over 4. So we'll do it again. So that's what follows next. And we'll inductively choose x sub n and b of 1 over 2 to the n minus 1, such that the vector y minus t of x of 1 minus t of x of 2 up through minus t of x of n minus 1, the old vector minus t of x sub n, that new x sub n that was chosen, the norm of that difference is less than epsilon. We'll choose epsilon to be r over 2 to the n. So same pattern we had above. To put it in the context we had on the previous slide, we're taking k to be n minus 1, this n minus 1 right here, and we're taking epsilon to be r over 2 to the n, the r over 2 to the n here. Oh, and we can rewrite this. Let's use the linearity of t to rewrite this as y minus t up, x1 plus x2 up through x sub n, because t is linear. Let's give that an asterisk because we're going to use that again. Hypotheses, we haven't used boundedness, and we haven't used the fact that we're in Banach spaces. We're about to use both of them. Norm of x sub n is strictly less than 1 over 2 to the n minus 1, right? X sub n is chosen from the open ball of center 0 and radius 1 over 2 to the n minus 1. So we get the norm of x sub n strictly less than 1 over 2 to the n minus 1. Let's try adding up the series from n equals 1 to infinity, norm of x sub n. So we've created a sequence of x sub n's. Let's try to sum their norms. Well, each x sub n is less than 1 over 2 to the n minus 1. So this series is strictly less than this series. Replace the norm by this known strict upper bound, making a big deal out of the strictness because somewhere along the lines we're going for open balls. This is a geometric series with first term 1 and ratio 1/2. That'll sum to 2, which is a little unfortunate. We'll have to cut something in half before we're done. But this sums to 2. First observation is, well then, if the sum of the norms is finite, then that series is absolutely convergent. We said in a Banach space, absolutely convergent series are convergent. or we said maybe it was in a complete metric space. But we've dealt with absolute convergence and convergence before. It needs the completeness. We got the completeness because we've got Banach spaces, check. So now we've used that hypothesis. The only thing we haven't used so far is the boundedness of T, and we're about to use that. All right, well, if that's a convergent series, then it converges to something, call it X. So let X denote the sum of that series of X sub n's. By the triangle inequality, the norm of X is less than or equal to the sum of the norms of these things in this series over here. All right, it's a triangle inequality induction and some limits, but this is not a surprising claim here that we get the less than or equal to. Oh, and we saw that the sum of the norms is strictly less than 2 from above. Okay, let's apply transformation T to vector X. T of X, that's T of this series. Is T of the series of the T ofs? Can you take that transformation inside that series? Well, series is a limit. It's a limit of the sequence of partial sums. Can you take limits in and out of this transformation? Because that's what you're doing when you move the series from inside to the outside. You can if it's continuous. Is T continuous? T is bounded. There's the bounded hypothesis. And bounded linear transformations are continuous. That's what theorem 2.6 was about. So if it's continuous, yes, you can bring limits outside. Yes, you can bring that series stuff outside because it's a limit of a sequence of partial sums. So we've got a sum from 1 to infinity of T of X sub n. We're claiming that equals Y by this inequality here. What we have is Y minus T of a partial sum is small. You can make this as small as you want by making n large. So this is playing the role of the epsilon here. So the larger n is, the smaller this is, the closer together Y and this T of thing is. In other words, the limit here is Y. So the asterisk equation establishes that that series converges to vector Y. Okay, we're looking for an open ball that's a subset of T of B of 1. We seem to be kind of wandered off into the weeds here, but we'll come back. All right. We've got X of norm, strictly less than 2. So it's an element of a ball of center 0, radius 2, B of 2, as we've denoted it. And we've got Y equals T of X. Okay, well then Y is T. Y is an element of T of B of 2. If X is in B of 2, then T of X is in T of B of 2. Y is an arbitrary element of B prime of R from 2 or 3 slides ago. And we'll go back and look at that in a second. But we have taken an arbitrary element of B prime of R, and we've shown B prime of R as a subset of T of B of 2. That's almost exactly what we want. I don't want radius 2, I want radius 1 to use the stuff in step 1. No problem. If this is a subset of that, 1/2 of this is a subset of 1/2 of that. Dealing with sets of vectors, such manipulations make sense. You can take these scalars inside to modify the radii. Lemma 3.4 part D. So we get B prime of R over 2 as a subset of T of B of 2 over 2, T of B of 1. And that's what we were looking for. So there is an open ball of radius, it's called delta R over 2. Open ball of radius delta that's a subset of T of B of 1. If we could find that, step 1 told us that T of U was open. Okay. There's only, 6 slides of arguments. We had a picture. It's elaborate and full of details, but really, we started with a ball of radius s. To deal with this vector z, we had to cut that radius in half. We chose z from this ball, so z from b prime of s over 2. So we've taken that radius s and cut it in half to allow us to access this z parameter as needed. And what we got from that was let's see, previous slide, here it is. What we got from that is b prime of s over 2 was a subset of t of b of 1 closure. I got to get rid of the closure. What we did is we took r and cut it in half. So we ended up cutting the radius in half again, and we had delta equals r over 2. Cut in half again. I was going to look up where we made a big deal out of an arbitrary point. Here it is right here. Continued 3, slide number 6. We assumed at this stage that y is an arbitrary element of b prime of r. And then we went through and showed that that implies that y was an element of t of b of 2, and then we cut that in half again to get the unit ball. So there's geometry behind it. It's not quite as wild as it might look on the surface of things. So that finishes it. And that's the open mapping theorem. So surjective, that is onto, bounded linear operators map open sets to open sets, the open mapping theorem. Continuous functions don't do that. There's an analogous result concerning analytic functions in the complex analysis setting. But there's the open mapping theorem. That takes care of this section, one statement and a lengthy proof. I'll see you in the next section shortly. Have a nice day.